So let's begin. As I mentioned on our schedule for the week, we come to the part of the course where you grade me and the course. So we'll take 10 minutes at the beginning to do that. I have to tell you that these things are very valuable to us, to me in particular, to help us evaluate how we're doing. I'm very self-critical myself, but I like to hear it from others as well. Here's one. Could you pass it down? There's people here. So take about 10 minutes to put down your thoughts. I don't know if there are enough there, maybe. Okay, thank you all. Maybe give him one too. Thanks. Oh, how you? Sorry. Sure. Hi. You got one? Everybody got one? Extras, good. Okay. Did I miss you? You're under my nose. need a class evaluation. So, if you would, please. Do a class evaluation, please. And I have to ask a favor of us. I'm not allowed to see these things until after you get your grades. Not that I know who's writing what, but and we wouldn't play favorites, of course. But some student has to bring these up to the office. Would somebody volunteer to do that at 4 o'clock? Very good, thank you. So kind. So let's collect them. Don't fold it. We're going to put them back in this envelope. And the box for this is on the left side as you go into, you know what 386? You know where it is. So if you maybe pass them one way and we'll collect. If you're still working on it and hand it in a little later, that's okay too. Please give it to her. Okay. Thanks. Thank you. Try to get the right side up. Right side up. Okay, I'll put them in the envelope. Thank you. Thank you. Yeah, the next one? Okay, fine. Good, okay. Okay, let's move on then to some more material here. Thank you. Well, we're going to talk about solids today, which is an abbreviation of chapter 37. I think the early part of the chapter has to do with bonding in molecules, for starters, which you will have learned a lot about in chemistry. It's a very interesting subject. The only part of bonding that I would bring to your attention for our purposes is that you can learn a lot just from the basic principles that we've shown about wave mechanics. Wave mechanics helps you understand bonding very well, because we know that, for example, atoms have the lowest energy state, typically a wave function that looks something like this, psi of the 1s state, and it gets more and more wiggly as you go up. I've emphasized that numerous times. And you get things like that. The radius of the atom goes up as the orbital numbers go up, and we can put down some qualitative things about them. For example, the Bohr. Let's think as an estimate of where to think the electron is. It's helpful to think of the Bohr radius, because the Schrödinger theory gives you a variety of radii, actually, because in the second level, n equals 2, you have both s states and p states, and their radii are different, so that although the energies are the same, that's the interesting thing. The energy of all these levels, in n equals 2, all the L have the same energy. All L have same energy. In the hydrogen atom. In other atoms, it isn't quite so. That's the rule is broken, but they're roughly the same. In fact, in X-ray work, where the energies are quite very far apart, you can forget about the difference between S and P, and they just talk about a K shell, an L shell. They use a different notation, KLM. And all the L electrons, meaning S and P, are given the same energy because the differences are small. And of course, when you get up to the third level, n equals 3, or the M in X-ray notation, we haven't really mentioned that too much, but it's just different fields develop their own notation. The atomic spectroscopists, starting at relatively low energies, at small atoms, developed the notation S, P, D, and so on. And n equals 3, S, and you have your S states, your P states, your D states. The X-ray people call that the first level K, second level M, third level M, and so on. So the point is that there are different radii, but if we take as a rule of thumb the radius of the largest L value, because that one will be most classical. As we've said, the higher the quantum number, the more classical, and it'll be the closest to the Bohr orbit radius as a ballpark estimate. And the Bohr radius goes as the quantum number n squared times the lowest one, and it goes inversely as the charge squared. So that's something interesting to notice. Now, is it reasonable? Now, as n goes up, it means you're at a higher energy state, and the electron is going in a larger orbit, sort of like the planets go in a larger orbit, and their angular momentum is going up as n. But the Bohr radius is going up as n squared of that high n state. The angular momentum of that state being n h bar. So that's one thing. As they get larger, and as I mentioned last time, the velocity in that state actually goes as the velocity in the Bohr state, inversely as n. But in any case, the one thing you see is that the radii get larger the higher the n state. And the thing that also happens, though, it goes as the charge on the nucleus inversely as the square. That's because if you have a heavy element, the nucleus has Ze charges, and when you work out the Bohr radius, the energy goes as Z squared e to the fourth. So, and in fact, the radius then goes as, this is the energy goes as that, but it'll turn out that the radius goes inversely as the square. And that's very interesting because what it says is that, for example, the one example I worked out, and it'll be interesting because copper is a very common metal, good conductor, and we'll be talking about good conductors here. The radius, you see, of copper in a high L state, its biggest orbit. The radius of the orbit, if you divide, and copper is the element number 29. So if you put in Z squared, that's roughly 30. So the radius of the orbit of copper is, let's say for n equals 1, you have the Bohr radius, and then you divide by Z squared. Now, Z squared being 29 is roughly 30. 30 times 30 is like 900. So the Bohr radius of the largest of the this is the n equals 1 state. So that is not the largest. But so this is the inner state of copper. And so it is 1,000th, roughly, of a Bohr radius. It's very, very tiny because the charge is so large, it's pulled the electron way into a tight orbit. So if you start out with a carbon, let's say a hydrogen atom, it has a Bohr radius A0. By the time you get to copper, the Bohr radius is 1,000th as large. So it's really tight in there for that low state. So what the point of this is that if you had a lattice of copper atoms, the lowest states are so tightly pulled in that they don't touch each other in neighboring atoms, because there are other electrons way out here. Yeah, they reach out, but the inner ones don't. So the inner ones don't interact, so they don't even know they're in a lattice. They're so scrunched in that they just don't participate. It's the outer valence electrons, which are big enough to sort of touch each other and also to feel or even detach from the copper. But these guys in here are held in very tightly. Now you can get them out because if you hit them with enough energy, like with an electron of a high voltage, EV, of energy, big enough, you can knock these copper electrons out of the 1s state and create an empty state there, and you can then see the X-rays that will emanate from a copper target when other electrons, seeing an empty state here, drop down. In fact, what you'll get is, for example, we call that the K. Let's say you knock an electron out of the 1s state, or the K level, as the X-ray people would call it. If an L electron drops down, you get what's called K alpha radiation. That's the radiation K going from L to K levels. So there's the connection there. But what I'm trying to say, first of all, with all these other ramifications that come out of this simple idea, is that those inner electrons are very much scrunched in compared to a Bohr radius, and they mostly do not participate in the bonding because they are so far away from other electrons that they don't even feel them. So that's the first lesson here, I would say. Okay, there's other aspects of the Bohr radius that is interesting. Let me see. I think I'll save that for when I just discuss semiconductors, because it comes up again there very strongly. Yeah. Okay, so the point is, when does the bonding actually occur? And that's when the atoms' electron wave functions touch each other. And so they interact, and you have additional, so in addition to the central force of the nucleus acting on the electrons, if you bring another atom close enough, you have other forces now acting, and they can either repel each other or they might attract. And in fact, what we find in many cases is that the overall effect is an attractive one, and we have solids, molecules as well. And one way of looking at this is, I think you may have seen this in chemistry, where let's make a simple model of a atom as being just a deep well. And this is another atom over here, let's say far away. Now, we've done the states. Now, this is a finite barrier, which an atom would be. In other words, you can get an electron out of this, not an infinite well. So there will be a little bit of tunneling into the barriers, and then the lowest state will look like this, the usual familiar thing that we've done a few times already. And you'll have a wave function that looks like this on the other side. And as I say, if these things are far apart and the wave functions don't touch, even the tails don't touch, they don't change each other. On the other hand, when you bring them closer together, you will get that the wave functions interact so that this electron in here feels the presence of the electron over here. Their wave functions touch. Now, the interesting thing is partly that if you have a wave function in box 1 and one in box 2, the wave function, so far, we've written it and always drawn it positive. But when you have two of them, the possibility occurs that one of them could be considered negative, having a negative sign. And that doesn't really change anything, because even if it were negative, the thing that counts is psi squared. So if we took psi positive, you square it, you get psi squared. And if you have it negative and you square it, you get the same psi squared. So offhand, both of these are possibilities, and they don't change anything. They do change things when they touch each other, because then the possibilities are two. Namely, suppose I make that tunneling barrier, the barrier or the approach of each to the other very thin, such that the wave functions overlap, like so, you see. Now, this electron is capable of tunneling into the other one. So now, or you could have the possibility that one of these is negative. And it's possible to say, something like that. Now, it will turn out that these two possibilities, now the fact that one is negative makes a difference, because these two energies of these two possibilities are different. It will turn out that this energy here is lower. And then this one. So it'll turn out that the electron wave functions add up in a positive to positive. Now, the justification for that, let me put it over here. This case A is lower than in case B here. The justification is, let's see what happens if we sort of make the barrier thinner and thinner till practically it's gone. Then these two, adding positive to positive, end up with a bigger well, and you have basically one wave function. And the way they've added positively, they end up with one positive thing. And this is another, extension or limit of that barrier case. Whereas this fellow, when he adds up this with a negative one coming from the other side, is ending up looking like this. So, and we've learned that the fewer the wiggles, the lower the energy. This has a higher energy because its wavelength is shorter. So the energy is higher. So that's the way we go from isolated atoms to molecules. For example, this would be the hydrogen atom wave function. Hydrogen 2 wave function would tend to look like this in the ground state and would be bound. And this is the way it looks in the more excited state, the antibonding orbital, as it were. And so the thinking like this goes on. If you're thinking of bringing atoms together to form molecules or solids, now in solids we have yet another approach based on quantum theory, especially for highly conducting materials where the electrons, say in copper, they seem to be very free to move. You put a voltage on and the electrons move very freely. You get, in a wire, we say there's not even any voltage drop. There's no energy loss. The electrons don't do anything by giving up energy much in a wire. So an approximate, I just mentioned this just to show you how physicists think. They go from one limit, namely start with atoms, bring them together, see how they overlap, and see who pushes whose energy level up or down, and that will give you a bound state, or the new condition of the molecule. The other approach comes from the other point of view where we say the electrons are almost free. So let me think of the solid block of copper as a box, and let me put electrons in that box. Start with them free. So then you would start, then you go back to the same picture here, but now you're thinking about the copper as a single block, and a wave function would look like that in the whole copper block. Why not? It's an approximation. And then you build up other wave functions. You know, you have 2, and then you have 3 and 4 and 5, and you build up waves inside the whole copper block. So that's actually called the free electron model. And I just mention it as a way of showing you how physicists think. It's nice to try two extreme cases and see what happens as you sort of come to the middle, and maybe you'll have the right answer. And that's maybe a good way to think about how to approach problems once in a while. Now, that's about all I really want to say about where bonding comes from and where we get carriers. The point being that if you have something like copper, the inner electrons do not touch each other very much. The outermost electron is relatively weakly bound. Its energy is going, did I write it down? Its energy is going as some basic energy over n squared. So that in a high energy level, also it goes as z squared actually too. But in a high orbital number, the energy can be pretty weak, such that the electron is basically free. And then we have conductivity. We have seen, now I'm going up to the slides here, and we have the thing we've seen before is Ohm's law. And actually previously I've talked about where does resistance come from. And the resistance, we have had the formula before, is rho L over A, which is if you have a shape with an area of that object and its length, the larger the area, the less will be the resistance because there's more space for the charges to get through. The longer the object is, the harder it is to get through because this is a somewhat clogged pipe. And so the more you have to go through it, the longer you go, the harder it is, and so the resistance goes up. And then the resistivity has to do with the particular material in the block, which has to do with the electrons trying to get through and bumping into the material. Different materials are different, and we'll talk about that. Now, I did have this demo, I think I did it before, where we have these nails which represent objects. Now, the nails actually, if you look at it, they're really in a quite nice row here. If I could roll down in between, I think they would pass very nicely. But because of gravity, it looks kind of like an obstacle course. And of course, the point is that it goes relatively slowly because it's bumping into things at all the time. Much slower than if I just simply drop like that, you see, which is going the same height. The potential energy here is the same whether I'm going this way or that way, but the fact that there's no obstacles means that the ball can grow. But so there's one thing is the number of obstacles, that is how bad this material is. The atoms are out of place. There are boundaries. Sometimes you have a crystalline material and there's two, what they call grains of material. Now, you can make materials, and we'll talk about silicon. They can make silicon so pure that there's no imperfection in it, like 1 part in a billion or trillion out of place, because silicon is a very important material, and they really know how to work on silicon. So you can make them very, very pure if you try very hard, and if it matters to you, like in silicon's case, it does. But most things like copper wire, you just draw the wire out, and it's got boundaries and grain boundaries and all kinds of stuff that'll think. But see, what's even worse is if the thing is at a finite temperature. Because suppose I let this ball down, and moreover I shake the thing, which is temperature. You see how much harder it is for the ball to get down. So this is the phenomenon of that the resistivity. This is a very important idea. The resistivity actually is a function of temperature. At very low temperatures, yes, there'll be some resistivity because of all the, imperfections of various kinds in the material. Static imperfections. Yeah, that's what I should have said. Static imperfections, like the nails being not in a smooth way. So you have that even at the lowest temperatures. But what gets worse is that if the temperature goes up, you get a temperature dependence of the resistivity. So this is due to heat motion. So this is the typical behavior of metals in particular. It's not, but we have to go a little bit deeper actually to see that, to understand semiconductors. See, metals are relatively easy, but we can derive here, I hope I have that. Yeah. So I think maybe I've done this before, but you can derive just by the idea that there is scattering with a time tau, and so the particle is accelerating because of, in the case of that demo there, because of gravity, there's an acceleration downward due to mg. That's the force. And but there's a scattering every time it hits one of the nails. And so you would replace EE by mg, the force here, if we're talking about that demo. And there's a time. And so, and also, the other thing that would increase the current here is if I put in more than one ball at a time. Yeah, now clearly the current is higher there. So it depends also on the number of charges that you put through. So the final formula for the conductivity of a material is the number per unit volume, n, E squared, the charge that it's carrying, the scattering time. If the scattering time is long, this is now, interestingly, sometimes easier to think about the reciprocal of the resistivity. This conductivity is how easy it is. Resistivity is how hard it is. And so the conductivity goes up, as you would think. It'll conduct better if I have more carriers. The stronger the electric charge is, the longer the time between scattering, and inversely is the mass, because the mass is kind of an inertia and it's holding back the flow. So what you have is this velocity picking up, scattering, picking up, scattering, the electric field pulling the thing along. You get this average drift velocity. But what I want to call to your attention, there are two parameters here that we can play with. We may have some control. Well, over tau, the scattering time, we could have some control by making the crystal more and more pure and perfect. Take out out of copper, we take out the zinc, we take out the whatever else, manganese, whatever else might be in there, which it might be different and might scatter the electron, because the electron wants a nice regular array. And also, so those would be you could fix up tau. You could also lower the temperature and get better resistance, or less resistance, or more conductivity. But the other factor that is working in semiconductors, it turns out, that you can change the number of carriers. In a metal, you can't do that. In a piece of copper, the number of carriers, and this is a very important formula, so maybe I should write it down someplace where I want to erase it. Sigma, the conductivity is N, again my N's, E squared tau over M, the mass. And so this is the number of carriers, and this is the scattering time. This is an intrinsic property. It's 1 over it's the inverse of the resistivity. Okay, now, actually, I think I may have said almost enough about metals. But the question, one of the big questions that quantum theory answered was the question of why are there metals and why are there insulators? Why are some things like rubber, you put that on the outside of the wire to keep you from touching the metal, and the electricity does not go through the rubber on the wire, but if it cracks and you touch the metal, you can get a shock. Why is rubber different from copper? And the answer happens to be, well, again, there are these two pictures. You can start with atoms and build up a solid conductor, copper, or you can start out with a rubber molecule and build up, or you start out with carbon even. Before you even get to rubber, you start out with carbon and start building rubber. But the point is that in any case, you start, let's say we start out with the atomic, at the atomic level, or you could start out with the free electron. If you start out with the atomic level, you start out with 1s and then 2s, 2p, and 3s, 3p. Now, as we saw, if you bring atoms together, they push each other's levels around. So what you get for every atom you put into the thing, you get a slightly different level. So you get this band of levels, one from each of the atoms that you're involved with. So we call that the S band. It has nothing to do with rock music, by the way, but it could. Then you have a band that starts out when the P levels. Now, as I say, in most materials, the S electrons are so tightly held that the broadening is not much because they don't feel each other. The P level, the orbits are a little bit bigger, and you might get a little broader band. When you get to the outermost levels, the electrons overlap their atomic wave functions, and you get a broader band. Okay, so now the idea simply is that if you have empty states in the band, and when you build a solid, you put electrons in these by the Pauli principle, the lowest states first. So typically you will fill the 1s state, you'll fill the 2s. Well, let's say you start with hydrogen, you fill the 1s state. Now, make a hydrogen solid doesn't happen very easily because there's too much, it's too light actually, and it moves. It's hard to make a solid of hydrogen or helium. But you can make a solid out of lithium, which has two 1s electrons, and it has a 1 2p electron. So it fills but there are two allowed levels in the P state, even in the 2s state. There are two levels in the S states, and then you have all your P states. So lithium, we're having two possible levels in the 2s state. It fills one of them, one is empty. Well, the key point is, if you have empty states in a band, it conducts electricity because the electrons can pick up energy and move through the band. It's sort of like a highway with space between the cars, or an extra lane. It's more like having an extra lane in a highway. So even if one lane is full, if you want to pick up speed, you can go into the other lane and you can move through. So what you have is, if you have what's called a partially filled band, you can have conduction in that band, because the electrons can always go into sort of the empty states and move along. You get insulators when the bands are full. If the bands are full, then the energy you need is the amount of energy to get into an empty lane is what's called the energy gap. It's the difference between these original states, which can be very large. And so for material where the energy gap is, let's say the order even of an electron volt. See, the point is you have good old KT trying to excite you into the next higher state, but KT at room temperature is really very small. That is, KT has an energy, this is the old story, of about a 40th of an electron volt, which is, I think, 25 milli-electron volts, if I do the arithmetic right. The point is that thermal energy is not enough to get you to the next state. And so if that's the case, the electrons can't move. They're stuck in a traffic jam, and they have no extra lane, and you have an insulator. You have a material that has no carriers. What's happened to make them an insulator is that N is 0 in a conduction band. You can have a lot of N's in the material, but you need some where there is a freedom to move. Now, the wonderful thing about semiconductors, which I'll try to get onto right now. So here's the story on bands in my PowerPoint. It's also in the book. The point is, an insulator has a big gap between states where there are electrons and states where they could move. And you have to put a lot of energy in. Now, you can do it with shining in strong light. For example, if you had a light whose energy was equal to Eg, you could lift an electron out of the valence band where they're full to there. Now, the other extreme here is the metal, where there is within a band some empty states. This is your free traffic lane. And so the electrons can pick up energy in electric field and move along in the metal. Now, what you do, now the semiconductor is sort of in between, but the nice thing about semiconductor is that we can change the number of carriers in a semiconductor. See, in the intrinsic semiconductor, the gap is pretty big. It can be about an electron volt, which turns out to be a temperature of 1,000 degrees maybe. We know that from the visible light is about needed. You need 1,000 degrees or a few thousand degrees to get visible light, and visible light has an energy about a volt. So visible light is able to lift an electron from this gap to this. But temperature isn't. Temperature is way down. Temperature is not a volt. It's a 40th of a volt. So you have very few carriers that are thermally excited from here. But you can, as I say, you can shine light in and have that happen. So what they've done is this clever, very brilliant thing that was devised in the late 40s, wherein you put donor and acceptor atoms in the silicon. What does that mean? Well, fortunately, you can understand this by the Bohr picture. See, what you do is silicon normally has 4 bonds to other silicons in the silicon crystal, just because of its position in the periodic chart. Now, what you do is you substitute for silicon. Let's say, now silicon is in column 4, it's 4 bonds. What you do is you substitute an element from column 3. Oh, well, let's do column 5 first. 5. And the classic case is phosphorus. Phosphorus has 5 electrons. Has 5 electrons. 4 of them go into the bonding. And it's interesting that the 5th one goes into basically a Bohr orbit, if you will. Again, you can do this quantum mechanically, but good enough to do it for here. So here are your 5 phosphorus electrons, and one of them is in a Bohr orbit. Now, what we said is that the Bohr orbits, and here's where I should remind you that the formula was, it had in it K, the constant for the 1 over 4 pi epsilon naught. But you see, now the electron is not in free space. So instead of epsilon naught, we said whenever you have a material, you should multiply this by this dielectric constant K. So you have to modify what this electron that's circling the phosphorus sees. It sees silicon. It doesn't see a vacuum. And the K of silicon turns out to be something like 12. So this weakens the electric force. So the orbit gets larger. And the radius then also, the radius of this Bohr orbit also depends on this kappa. And I forget, I'm not exactly now whether it's squared or what. In any case, the Bohr orbit gets to be very large. And the material is screening this out. So it turns out that the electron held by the phosphorus atom has an energy below the conduction band that's very small. It's around a 50th of an electron volt. So what that means is that with a certain modest temperature, you can get this electron to be ionized. And it goes off as a negatively charged electron. So this phosphorus is called, for this reason, it's called a donor, because it donates electrons. And a material in which you put these donors is called an N-type, that is negative type of semiconductor. We call that an extrinsic, because it is not intrinsic to this material. We've made it a conductor by extrinsic means, by artificially introducing these phosphorus atoms in very precise amounts. And the alternative to this is you can put in there a chemical element which is from the third part of the periodic chart, like boron. And boron in silicon has 3 electrons, and missing is one of the bonds. So we call that a hole. And it acts like a positive charge. It's like a positive electron, because what happens is that you have your other silicons over here, and what happens is that this hole can be filled by an electron coming from another bond, and the hole moves. So the hole moves like a positive charge. So you have these two types of materials. You have the this is called positive type, p-type, and the n-type. You might have heard of this before. Well, I think it's just 4 o'clock now. We have to stop. I think I'll continue on this a little bit because I'd like you to see, because I find it pretty marvelous, what the people have done in using P and N-type silicon semiconductors to create the modern electronics industry, computers, telephone switch lines, the fact that you could pick up a phone, dial Afghanistan, and it'll arrive at Afghanistan immediately. The right person answers in Afghanistan when you dial up. Don't you find that amazing? How, of all the billions of phone numbers in the world, that when I dial Afghanistan, the guy picks it up. And that's all because of this electronics. So, yeah, I think it's worth talking about on Friday. And then we'll do some more nuclear physics, too, because that's pretty important in our lives, too. Okay.